The majority of conics, again, the majority of conics is really just a bunch of formulas. Knowing the equations look like this, and then following all of these different formulas for that information. So for ellipses, we have this, and we have this. For parabolas in the previous, we have these two setups. Now again, we've gone through all this information already. We have. There's one more formula in this section that we want to talk about. Now, we actually have variables for A, B, and C. A being in regards to the major axes, B being in regards to the minor axes, C being in regards to the foci. I've got another equation for you. We're going to introduce a new variable being E. E stands for the eccentricity. Now, if you think of eccentricity, I hope you're thinking of the change, the awkwardness, the weird, the again, thinking of the root word eccentric. Okay, it's off the ball, off the cusp. It's different. Well, in terms of conics, it implies the roundness or the exaggeration of the change. So, in regards to an ellipse, this eccentricity is identifying the roundness of the ellipse. Okay, is it more curved like this, or is it more pointed like this? Okay, or is it just nearly ball-shaped? Okay, again, it's a matter of the eccentricity being higher numbers. Is it this, this, or this? Well, the eccentricity is specifically another formula. It's C over A. Now, think of how this corresponds. C over A. This is the eccentricity. If I ask you for it, this is what you're giving me. How does it make sense? Well, it is the comparison of the foci. Okay, it is the ratio of the foci length, the difference from here to here, in comparison to the difference from here to here. Notice if I have a center here, and this is my center, this is my center, this is my center, the ratio of this, my foci would be more like here. The ratio of this and this would be a lot different than this one, would be a lot different in this one. Okay? They wouldn't be as drastic. So, let's go ahead and look at the number 12 example for eccentricity. It says, find the eccentricity of this ellipse. This is the ellipse that I'm playing with. And it says, again, find the eccentricity. Well, how would I find the eccentricity of this ellipse? Well, first thing, I got to get this ellipse in standard form, dividing everything by 18. Now, I'm actually going to show this work unlike the last example that I went through. This thing is going to be 8x squared over 18 plus 9y squared over 18 is equal to 1. Manipulating this is going to be the same thing as x squared divided by, well, 8 over 18 is 4 over 9. Well, if it's 4 up here and 9 here, I'm going to go ahead and leave that for a moment. Plus, this simplifies to be a y squared over, well, 2, right? Again, 9 over 18 is just going to be 1/2. This thing here changes a little bit differently. Let me go ahead and manipulate this. This is actually going to be, I don't like this 4 up here, because it doesn't correspond to my generic equation of x squared over a squared plus y squared over b squared, or one of the forms of this. I want all the numbers down here. Well, let's just, move the number. If this is a multiplication up top, couldn't it be considered division down here? And if you don't believe me, change this to 9 over 4. X squared divided by this, flip change, flip the 4 back up. Hey, it's the same thing. So this is plus y squared over 2 is equal to 1. Now, which one of these numbers is larger? 9 over 4 or 2? Well, 9 over 4 is 8 over 4, which is 2, plus a 1/4. This one's my larger value. This one is what compares to a squared. So let me write this as a squared. So lastly, x squared is divided by 3 over 2 squared. Again, 9 is 3 squared and 4 is 2 squared, so 3 over 2 squared. Plus, this is y squared over the square root of 2 squared, and that's all equal to 1. This is the generic equation of my ellipse and the eccentricity formula. E is equal to c over a. C being the correspondence of the foci. C being the correspondence to the foci, and a. So I have a as 3/2 because that's the larger value. So I have E is equal to something over 3 over 2. What's this something? How do I find the C value? Well, remember, the formula that's very close to the Pythagorean theorem is C squared is equal to A squared minus B squared. So I'm going to have C squared is equal to 9/4 minus 2. Again, the A value, the B squared value, the A squared value, the B squared value. This here is just going to be a value of 1/4. Again, because 2 is 8 over 4. Like denominators, 9 minus 8 is 1/4, so this is going to be 1/4. The eccentricity of this, if I do keep flip change on it, will be a 1/4 times a 2/3, which is really just a 1/6. And that's what I'm looking for in that problem. Okay, that's the eccentricity. Now, if you want a stronger explanation of how that number identifies if it's going to be more eccentric or less eccentric, well, think of it this way. This distance, this 3 over 2, is not actually that far off from radical 2. I believe radical 2 is approximately 1.7 something maybe, and 3/2 is approximately 1.5. They're relatively close together. So my eccentricity is a small number, which means that it's going to look closer to this. It makes sense for the higher the eccentricity, the more elongated this information is going to be. Okay? So that completes question or example 12. We're going to skip example 13, and the reason for that is because we would have to define a few things in terms of science. For instance, the perihelion or perihelion distance. I don't really care to define that. If you wanted to look it up, it is in your textbook. They do have that defined in there. Okay? What I'm going to talk about is actually the application example of number 14. I think these things are probably some of the coolest things we have that apply in terms of ellipses. Now, don't get me wrong. Orbits in terms of Earth, Saturn, Mars, any moon of those, they're all in an ellipse orbit. But they're harder to consider in terms of, just ridiculous numbers, 93 million miles and 91.5 million miles. They're just very, very long distances. What I'm going to talk about is the room that is 88 feet long, okay, that is constructed to be a whispering gallery. Now, there's actually one of these up in, I believe it's the Capitol building in D.C., the whispering rooms or the whispering galleries are specifically the rooms where if I'm standing, and I'm going to go ahead and draw a picture of this, okay? It's a room that's got a dome that's an ellipse-like. If I'm standing at one of the foci in here, your whisper will move from this point. It'll bounce off the ceiling perfectly so that this person standing over here will hear your whisper like they're standing right next to you. Okay. Again, there is one of these rooms, I believe, in the Capitol building. If you're standing in one location and you whisper and somebody else is standing here, they will hear you like you are whispering in their ear. And that's because of the way the ellipse, okay, bounces in this way. Okay. It is very cool how this actually works. Okay. Now, with that being said, let's go ahead and try in this actual example. A room 88 feet long. From here to here is 88 feet, is to be constructed to a whispering gallery. The room has an elliptical ceiling. There's your elliptical ceiling. If the maximum height of the ceiling, so way up here above the centerpiece, is 22 feet. Again, from here to here, this right here is 22 feet. Determine where the foci are located. So where are these two particular points? Well, let's visualize this as though it was just an ellipse, not a flat floor in terms of room. If this was just an ellipse, and I'm going to center it at the origin, this distance from here to here would be 44, because from the base, if a person was standing right here in the room, this to here would be 22. Okay? The distance from here to here would be 44. Why would that be 44? Well, because the whole room is 88. Well, if this is the case, where is he standing so that his buddy over here, yes, I'm drawing the picture, I don't care. where is he standing in correspondence, okay? Where this person can whisper, this person can hear, and vice versa. What is that point? Where is that location, okay? Well, if that's the location I'm looking for, what I'm going to do is this. I know that that value is a distance of c away from the center. If I put the center on the coordinate plane such that it's a 0, 0, I'm just looking at a squared minus b squared is equal to my c squared value. I know this to be true where a is the larger value and b is the smaller value. Out of the two values that I have in terms of the distance for a or b, which one's larger? This one is. Okay, so that means I'm going to have c squared is equal to my a squared value, 44 squared, minus my b squared value, 22 squared. Okay, now if I were to actually go ahead and multiply those out, we're going to get 44 times 44 is 1936, and 22 times 22 is minus 484. So I have those two numbers subtracted from each other. And I did that wrong on my calculator here. Give me 5 more seconds. I have 1936 minus 484. We get 1452 is equal to c squared. So then what is the square root of that number? Well, the square root of that number is approximately 38.105. Now I'm going to read this question again. Determine where the foci are located. It doesn't tell me to round. So what I'm going to do is I'm going to say it is approximately 38 feet from the center of the room. Okay? That's what I'm going to say as my solution. It doesn't tell me to round. It looks like it's approximately 38 feet. So from the center of the room, I have to walk 38 feet, okay, towards this other end, and 38 feet towards this other end, and then you can whisper back to each other. Now, I believe in the Capitol building that they actually have this room in. They actually have stars on the floor of where you can be standing so that the other person is going to hear you on that other point. I believe there's stars or something. I don't remember. But this is, again, like I said, I think the coolest application of the ellipses that you could possibly see. The next video, be prepared for hyperbolas, which are just a bunch of other more formulas.